निर्माण नो अभिगम कल्याण हो छात्र नो हरदम उच्च अभ्यास नो शिक्षण धाम महर्षि गुरुकुल महर्षि गुरुकुल महर्षि गुरुकुल महर्षि गुरुकुल महर्षि गुरुकुल.
In this session, we will be studying chapter 10, Circles from your NCERT textbook of Mathematics of class 10. We'll be dealing with the introduction part of 10.2, that is, number of tangents from a point on a circle. We will be dealing with how many number of tangents can be drawn from a point on a circle. From a point on a circle, then where the point should lie. Whether the point is inside the circle, it is on the circle, or it is outside the circle. So we will have to deal with 3 cases to find the number of tangents that are possible to draw on a circle at 3 different positions of that point. The very first position that we will be dealing is, suppose the point is inside the circle. Suppose the point is inside the circle. Suppose this is my circle. And this is the center of the circle, and there is a point out here somewhere. From here, we have to draw tangents to the circle from this point. This is my center that is given to me with O as its name for the given circle, and if this is the point that lies inside the circle and we need to draw the tangents to the circle, then how can we draw tangents to this circle? Is it possible? Let us check it out. From this point, suppose tangent is a line that touches only one point of a circle. Suppose from this point we draw a line this way. It should be extended this way also. That means the line passing through this point, this way, intersects the circle at 2 points. So this cannot be the tangent. Suppose we take some other line this way. Suppose this is the line L2, say previous one was L1. Again L2 line passes from our given point that lies inside the circle, but again it intersects the circle at 2 points. So this is also not the tangent. Suppose you draw another line this way, line 3. Then again this line intersects the circle at 2 points. So this cannot be the tangent. So generalizing, we can say that if a point lies inside the circle, the given point lies inside the circle, from that point no tangents can be drawn to the circle. That means if a point is lying inside the circle, tangent formation or making of tangents or tangent is not at all possible for that given circle. Now let us move on to the second condition. When the point lies on the circle, when the point lies on the circle. So again we are given with a circle with center O, and suppose the point lies on the circle. Suppose this is the point that is given to us. Then how many tangents can be drawn from this point? Suppose we draw this way. So this is a line that is passing through the given point, intersecting the circle at 1 point. That means this is the tangent that is possible. Are no tangents possible? Let us see. If you change the position of the line, suppose this way it moves, this way it moves. Again, this is same line as the previous was line L1. Now this line L2 intersects the circle at 2 points. So this cannot be the tangent. So moving on this way, we can generalize that if a point lies on the circle, from one point, one tangent is possible. In the previous section also I have told you that since there are infinite number of points on a circle, so infinite number of tangents were possible. Now, if one point is given on the circle, that means if it is on the circle, only one tangent is possible to draw, and that tangent is L1 and not this L2. This is wrong. Only one tangent is possible, and the tangential line is L1. Moving on to the third condition. If the point lies outside the circle. The third condition. Outside the circle. So we are given with a circle with center O and a point lies somewhere, say that point is P, that is lies outside the circle. Then how many lines can be drawn from this external point to the circle? How many tangents can be drawn from this external point to the circle? So if we draw this way a tangent, it will intersect the circle at one point. That means from here, if we draw a line intersecting the circle, this line will intersect the circle at one point to form a tangent. If we move this side, again this line will touch the circle at one point to form a tangent. That means from an external point, that is from a point outside the circle, two tangents are possible to draw on a circle. From the point that lies outside the circle, external points, whatever we say, it's the same thing. So from a point lying outside the circle, two tangents are possible. Naturally, we will be concluding that if a point lies inside the circle, no tangent formation is possible on that circle. If the point is on the circle, then only one tangent can be drawn to the circle. Now, if a point lies outside the circle, there are two tangents possible to draw from that external point to a circle. So, the number of tangent formation that we have seen for different position of points, whether inside the circle, on the circle, or outside the circle. Then here follows a theorem. The length of tangents drawn from an external point to a circle are equal. That means external point. That means the tangents are drawn from the external point to the circle. And how many tangents are possible to draw? Only two tangents are possible to draw. So we are given with a circle with center O, and we are given with an external point. So the external point is P. The length of the tangents drawn from an external point to a circle are equal. So we have two tangents. So let us draw the two tangents. This is one. This is the second tangent. Say P and Q. These are the two points of contacts of the tangent from an external point P to the circle with center O. And we need to prove that the length of the tangents are equal. What do you mean by the length of the tangent? The length of the tangent is the distance between the external point P and the point of contact P or the point of contact Q, whatever you say. Is the distance between the external point till the point of contact. This is called length of the tangent, and we have to prove that both the tangents are of equal length. So let us prove it. We are given what we are given? We are given circle with center O. PP and PQ are tangents that is given to us, and we need to prove PP is equal to PQ, that is the length of the tangents should be equal or are equal. We have to prove that. In order to prove, we need some construction, and the construction is join OP, OQ and OP. We have to join these two things. So let us join OP, then OQ, and then OP. We have joined. Now, as soon as we have joined OT, can we say that OT is perpendicular to PP? Yes, we can say. By theorem 10.1, radius and tangent at a point are perpendicular to each other. This we have proved in the theorem 10.1. Similarly, we can also say OQ is perpendicular to PQ by theorem 10.1, that the radius and the tangent at the point of contact are perpendicular to each other. So what we get from here when we join this, here follows our proof. So let us write that what we have got. Here we can say OT perpendicular to PT and OQ is also perpendicular to PQ by theorem N/1. Now we need to prove that TP is equals to PT. What we can do is, we can prove both the triangles to be congruent triangles. If we prove both the triangles to be congruent triangles, then by corresponding parts of congruent triangles, that is what we call it in short form as CBSE, corresponding parts of congruent triangles, we would be able to say that TP is equals to TP. But first we need to prove both the triangles to be congruent, and congruency can be proved using the congruence rules. We have four congruence rules that we have gone through, out of which one should be applied here. Let us see which one is applicable here. So in triangle OPT and triangle OPQ, we need three things to be equal for the triangles to be congruent, that too following the rules of congruence. So what are the three things that we can write? So first, can we say OT is equals to OQ? Yes, we can say both are radius of the same circle. So what we have got. Second, we have just by construction we have seen, by theorem 10 point we have seen that angle OTP is equals to angle OQP is equals to 90 degrees. So we can say angle OTP is equals to angle OQP is equals to 90 degrees. We can say from equation number 1, and we can use this one as equation number 1. So we have got two things. And the third thing that we can say, in both the triangles, if we see OP is common to both the triangles. So we can say OP is equals to OP, and that is common to both the triangles. Now we have got three things. Which rule is applied? Let us see. This is one side, this is right angle, and this one is hypotenuse. So we can say by RHS rule, the triangles are congruent. So therefore we can say triangle OPT is congruent to triangle OPQ by RHS rule. And when they are congruent, then we can say that PT is equals to PQ by CPCD, the short form for corresponding parts of congruent triangles. Hence we have got PT is equals to PQ. So what we wanted to prove has been proved. Example number 1. Prove that in two concentric circles, the chord of the larger circle which touches the smaller circle is bisected at the point of contact. So first of all, we should have two concentric circles. Two concentric circles means two circles are drawn with the same center. So suppose these are the two concentric circles, two circles. Say the name of the circle is C1 and C2. And C1 is the larger circle and C2 is the smaller circle. So in two concentric circles, the chord of the larger circle that touches the smaller circle. So the chord of the larger circle which touches the smaller circle. So when AB is the chord of the larger circle, AB is chord for the larger circle, and that touches the smaller circle, so it becomes a tangent to the second circle. Is bisected at the point of contact. So the point of contact here is say C, and we need to prove that AC is equals to BC. At the point of contact, that chord is bisected. Bisected means it is divided into two equal parts. So we have to prove that C is the midpoint of AB. That is the two concentric circles have a common center O. We have to prove AC is equals to BC. So let us start. We are given two concentric circles with center O. That is with common center O. You can also write that O. AB is the chord that is given. AB is the chord of C1, that is the larger circle, touching C2 and C. We need to prove what we need to prove. We have to prove that chord is bisected at the point of contact. That means we need to prove that AC is equals to BC, that C is the midpoint of AB. For that we need to do some construction. What we have to construct? We will join OC. We will join OC. Now as soon as we join OC, we can see that OC is perpendicular to AB. From theorem 10.1 we have the tangent and radius of the same circle at the point of contact. They are perpendicular to each other. So we can now say in proof that here OC is perpendicular to AB, and that is why theorem 10.1. This is only because of theorem 10.1. Now as soon as OC is perpendicular to AB, in class 9 also we have studied that a perpendicular drawn from the center to the chord bisects the chord. This was the theorem that we had studied in class 9, that a perpendicular from the center to the chord bisects the chord. So we can directly say that AC is equals to BC. So we can say imply AC is equals to BC, that is perpendicular drawn from the center to the chord bisects the chord. Perpendicular drawn from the center to the chord bisects the chord, that implies AC is equals to BC. Whatever we wanted to prove has been proved within two steps. So this is proved. Example number 2. Two tangents PP and PQ are drawn to a circle with center O from an external point P. We have to prove that angle PTQ is twice of angle OPQ. So let us first draw the figure for that. We are given with a circle with center O. This is the circle that is given with center O, and we are also given with an external point P. So let the external point be T somewhere here. And TP and PQ are two tangents. So TP and PQ are two tangents. So this is P and this is PQ. TP and PQ are two tangents. We have to prove angle PPQ. PPQ, this angle, is twice the angle OPQ. OPQ. So we have to draw that angle. OP and Q. We have to prove this angle is twice of this angle. So we can prove it. Let us consider this angle to be theta. Let angle OPQ is equals to theta. Now, we know if this angle is theta, then what will be this angle? This will be 90 minus theta, because OP is perpendicular to TP by theorem 10.1. OP is perpendicular to TP. This is by theorem 10.1. Therefore, angle TPQ is equals to 90 minus theta. We can say that this angle is 90 minus theta, and this angle will be 90 minus as it is. Now we also know, therefore, TP is also equals to PQ. This is by theorem 10.2. This is by theorem 10.2, that is the tangent drawn from an external point to a circle R of equal length. If TP is equals to TQ, so we can say implies PTQ is an isosceles triangle. If it is an isosceles triangle, then we can also say that angle TPQ is equals to angle TQP, and that is also equals to 90 minus theta. This is, keep this one as well. That is from equation number 1, we can say that. That means if TP is equals to TQ, then PTQ is an isosceles triangle, then this angle will be equals to this angle by the isosceles triangle property. And if this is 90 minus theta, then this is also 90 minus theta. Now we have got two angles in the triangle PGQ. Angle PPQ is known, angle PQP is known, and we need to find angle PPQ by the angle sum property of triangles. And we should get this one as 2 theta. If this is 2 theta, then only we can say that this angle is double of OPQ, what we have to prove. Clear? Then let us move. Then in triangle PPQ, angle PPQ plus angle TPQ plus angle PQP is equals to 180 degree. That is what is because of the angle sum property of triangle. So angle PPQ we are looking for. PPQ is 90 minus theta plus this is also 90 minus theta, and this total is equals to 180 degree. Simplifying, angle PTQ plus 180 degree minus 2 theta is 180 degree. If you take this side, angle PTQ is 180 degree minus 180 degree and plus 2 theta, and this cancels. Therefore, angle PTQ is equals to 2 theta, and we had taken angle OPQ as theta. So let us give this one. And we know, we can write dimension here, and we know angle OPQ is equals to theta. Comparing, we can say that angle PTQ is equals to 2 theta, that is equals to 2 times in place of theta we can write angle OPQ. Hence, so it's such an easy question where we had just tell you once again, we assume this to be theta. This total angle was 90 degree because of theorem 10.1, so this will be 90 minus theta. Then TP and TQ are the tangents from an external point, so both are equal. As these two tangents are equal, so it forms an isosceles triangle PPQ. Now if PPQ angle was 90 minus theta, then this is also 90 minus theta, and we just found out angle PTQ by the angle sum property of triangles, and we got that one as 2 theta, and that is double of the theta, double of the angle that we had assumed as theta, that was angle OPQ. Hence we compared and stated that angle PTQ is 2 times of angle OPQ. Example number 3. PQ is a chord of length 8 cm of a circle of radius 5 cm. The tangents at P and Q intersect at a point T. Find the length T. First of all, let us draw the. Suppose this is my circle, the center O. There are 2 points P and Q where the tangents meet on the circle. So this is my P and this is my Q and this is the chord whose length is 8 centimeters. So PQ is a chord of length 8 centimeters. If we draw the tangents at this point, they meet at the point P. It is given to us, they intersect at the point P. So let us make it a single point. So D is my external point. The circle is of radius 5 centimeters. So let us join and get this one as 5 centimeter. Radius is 5 centimeter. And let us join. Okay. Now this is what is given. PQ is a chord of length 8 centimeter of a circle of radius 5 centimeter. P is the radius. The tangents at P and Q intersect at a point P. The tangents at P and Q intersect at a point P. And we need to find the length TP. We need to find this length TP and this length B. That. And let us name this point as R and this will be R. And perpendicular drawn from the center to the chord bisects the chord. The total was 8 centimeters, so this will be 4 centimeters and this will be 4 centimeters. So the very first thing that we need to find is OR. So in triangle, let us write solution. In two triangles, TPO, okay, and first we need to find OR. POR, in triangle POR. Since it's a right angle triangle, by applying Pythagoras theorem, we can obtain the value of OR. So we can say OR square plus PR square is OP square. By Pythagoras theorem, that is sum of the squares of the two sides is equals to the square of the hypotenuse. So OR, we are to find the OR, so keep as it is. PR, we have 4 centimeters, so this is 4 square, and OP is 5, that will be 5 square. So OR square is equals to 25 minus 16. OR square is equals to 9. So OR is equals to 3 centimeters. Now we needed to find TP, so let TP is equals to y centimeters and PR is equals to x centimeters. This PR from here to here, let this be x centimeters, and TP we have taken to be as y centimeters. Now we will consider two different triangles, and by applying Pythagoras theorem we will be comparing the triangles and we will get the value of x and y. So which two triangles? So let us move on. So in triangle PRP. So in triangle PRP, this is 90 degree. So PR square plus PR square is equals to PT square by Pythagoras theorem. PR square plus PR square is equals to PT square. So TR square, TR was x. So this is x square plus PR square. PR was 4. So if you square it, this is 4 square and this is y square. X square plus 16 is equals to y square. Keep this one as question number 1. Moving on to the next triangle that we see is in triangle TOP. In triangle TOP, angle OPP is equals to 90 degree, and that is by theorem 10.1 that we know. So here in triangle TOP, PO is the hypotenuse and the two other sides are OP and TP. So applying Pythagoras theorem, we can say OP square plus TP square is equals to PO square. What is OP? OP is 5 centimeters. So this is 5 square. What is TP? That is Y square. And what is PO? Now the question is PO. PO means TR plus OR. TR we have taken as X and OR we had 3. So TO will be TR plus OR, that is X plus 3. So you can write directly here X plus 3 whole square. Substituting the value of Y square from equation 1 here and then solving would make the sum easier. So this can be written as 25 plus, in place of this Y square, we can substitute this part as X square plus 16 and this could be expanded as A plus B whole square, that is A square plus 2AB plus B square. So this is X square plus 6X plus 9 and the here reason we can give is from 1. We have taken the value of Y square from equation number 1. So this is this X square and this X square cancels. 25 plus 16, this is 41 is 6X plus 9. Then 41 minus 9 is equals to 6X. So this is 32 by 6 is equals to X. So X is equals to 16 by 3 centimeters. We have got the value of X, but we are not interested at all in the value of X. We are interested in the length of TP. That means we are interested in the value of Y that we have taken, that is TP is equals to Y. So substituting this value of X in equation number 1, we can get the value of Y also. So substituting the value, X is equals to 16 by 3 centimeters in equation number 1. We have Y square is equals to X square plus 16. In place of X, we can put 16 by 3 whole square plus 16. This is 16 square. What is 16 square? 256 divided by 9 plus 16. Taking LCM and solving. 256 plus 144 by 9. So this is 400 by 9. So Y will be equals to root under 400 by 9 and that is 20 by 3 centimeters. That is TP is equals to 20 by 3 centimeters, as TP we had taken to be Y centimeters. Now here the most important thing that we will have to consider is all the theorems are really very important to apply in the questions. The first we had used Pythagoras theorem and we obtained the value for OR. Then we assumed TP and TR to be Y of X, and then we took two triangles, two such triangles, two right angle triangles. Applying Pythagoras theorem, we formulated two different formulas comparing X and Y and substituting one in the second equation. We obtained first the value of X. Using that value of X, again we moved back to the equation number 1 where there was a comparison between X square and Y square. From there we have calculated the value of Y to be 20 by 3, and that value of Y was our TP that we were looking for, that is TP is equals to 20 by 3 centimeters.